Okay, let me start my second session of today's class with another exercise and a very interesting exercise. And also it is important in the sense that since you will be sitting for, the online test. So you may think that what sort of questions can be asked in in these online class or online tests. So actually I'm going to derive two formula, and on the basis of this formula, questions can be asked in the examination. Short questions can be asked in the examination. I am going to show you the derivation of this formula, and they are very important. So you be very careful while listening to me. Okay. So let me write the exercise. The exercise goes like this. Consider it to be a problem first of all. Let capital S be a finite set with n elements, then find out how many reflexive relations can be defined on the set capital S. Find out how many reflexive relations can be defined on capital S. I'm not going to ask any one of you about the result, about the answer to the given question, because we also very well know that nowadays the answers are also available in the internet. So you can immediately search the answer. You can look for the answer in the Google. You can type in the question, and the answers probably you have already got the answer. How many of the reflexive relations are present, are defined on S. The important part of the problem is not the answer. Answer is important because you have to recall, memorize it at the time of examination. But most important part of this particular problem is how this answer comes. So I'm going to explain this first of all here in this session. Okay, I shall not write many things, but I am going to explain it to you first of all. So we have the set capital S with n elements in it. Okay, what is this? In modulus sign I have written mod of S is actually called the cardinality of the set S. Cardinality of the set capital S. Cardinality means the number of elements present in capital S. Okay. Now we know that S cross S is the Cartesian product of S with itself. Okay, and the set goes like this: A1 comma A2 belongs is a collection of ordered pair of the form A1 comma A2 such that A1 belongs to S and A2 belonging to S. Okay, suppose since we have considered that S contains small n number of elements, so let us choose the element without any loss of generality. We are considering these n elements to be of the form A1 A2 AN. Okay, now if you like to write all the elements of S cross S, then it will be of this particular type. So we will be getting the elements of this type a1 comma sorry a1 comma a1 a1 comma a2 a1 comma a3 and up to this a1 comma an. Then we can get a2 comma a1 a2 comma a2 a2 comma a3 a2 comma an, and in this manner lastly we'll get an comma a1 a1 an comma a2 an comma a3 and an comma an. Okay, so we have got these many elements. How many elements will be there in S cross S? So it is quite clear from this particular picture that cardinality of S cross S will be n square. So n square number of elements will be present over here. Now I'm marking some elements, some special elements in this particular set. The special elements are marked as a1 a1 a2 a2 an like this. All the diagonal elements have been marked. How many diagonal elements are there? The diagonal elements present in S cross S is small n. And apart from these diagonal elements, if I do not consider these diagonal elements, apart from this, the remaining elements present in S cross S will be n square minus n. Okay, so we have got all this n square minus n elements are present, where diagonal elements have not been considered. Now the interesting part is that one particular thing you have to recall from your earlier knowledge, that if it's a recapitulation, that if capital A be a set with n elements, the power set of A contains all possible subsets of capital A, and in the power set 2 to the power n elements will be present. Okay, now for the set S cross S, if we design the power set then the number of subsets, sorry, let me write it in this manner. For the set capital S cross S with n square minus n elements, 2 to the power n square minus n subsets can be formed. Okay, for the set S cross S with n square minus n elements, 2 to the power n square minus n subsets can be formed. Okay, now I'm going to use one unitary method in this particular case. Out of these 2 to the power n square minus n subsets, one subset, acha, before that, we will write a collection. Let delta S represent the collection of all the diagonal elements. Okay. And in delta S, we have the elements A1, A1, A2, A2, AN, AN. All the elements are present. Now, one subset along with the elements present in delta S, along with all the elements present in delta S constitute one reflexive relation. Because you know that in to design reflexive relation, you should consider all the elements A11, A1, A2, A2, AN. Why is it so? Because in the reflexive relation, for the reflexive relation, it was written that for all A belonging to the set capital A row A must exist. Okay, so all these elements must be present for in the set for the subset to be for the relation to be reflexive. Okay, so one subset out of these n square minus n elements, you can consider from this, with this n square minus n elements, you can consider 2 to the power n square minus n subsets. Now, out of these 2 to the power n square minus n subsets, if you consider only one subset, this one subset along with all the elements present in delta S constitute one reflexive relation. So therefore 2 to the power n square minus n subsets, 2 to the power n square minus n subsets along with all the elements present in delta S constitute 2 to the power n square minus n reflexive relations. And that is your required answer. So how many reflexive relations can be formed from this particular set? 2 to the power n square minus n reflexive relations can be formed from the set. Okay, so you have to recall, I posed this as a problem. I gave you this particular thing as a problem. I asked you how many reflexive relations can be defined on S. Now you have got your result, and now it becomes your formula. Okay, so in the examination, you will be given a set capital S with say 100 elements, and you may be asked that how many reflexive relations can be formed on this particular set containing 100 elements. So if you do not know this particular formula, you will not be able to give the reply to the question. So according to this, the answer will be 2 to the power 100 square minus 100. That will be these many reflexive relations can be formed. If you want to check this particular problem with respect to examples, you can consider the sets. Say, for example, set S containing 2 elements, 3 elements, 4 elements, and you can write all these all these elements on a page and you can count them. You can count them. You don't have to put your attendance now. You don't have to put your attendance. Okay. You just listen to me. 65 participants, I can see 67 participants were there in the previous session. I'm noting this down. So anyways, so you can consider small n, you can consider this 2 elements, 3 elements, 4 elements set, and you can write all the possible pairs of S cross S, and you can count them, and you can correlate, you can relate the answer to the given, the formula we have obtained in this particular case. 2 to the power n square minus n is your required answer. And along with this, if I ask you, so if we consider this to be your question, example number 1, okay. Now, if I ask you that how many symmetric relations, can be defined on capital S, then you can do a similar mathematics on this. You already know that cardinality of capital S is n. You know that cardinality of S cross S is n square. And this S cross S constitute all the elements of the form which I'm writing once again for your understanding. A11, A1, 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 A2, A1, AN, A2, A1, A2, 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 AN, and AN, A1, AN, A2, AN, AN. Okay. Now, what was the symmetric property? Try to recall it. The symmetric property goes like this, that if A row B, then B row A. That was the thing. Or if A, B belongs to row, then B, A must belong to row. If you design a relation where these properties are satisfied, and it is true for all AB in the set capital A, then you can say that, yeah, I have considered all such cases and my relation becomes symmetric. Thus my relation is becoming symmetric. But if it is not satisfied, the relation is not symmetric. Now, we already know that if I do not consider these diagonal elements, by not considering these diagonal elements, these diagonal elements, n diagonal elements are present. We are left with n square minus n elements. Okay. Now, if we consider this to be in the form of matrix, then you consider in your mind that this matrix is the upper triangular matrix, and this is the kind of lower triangular matrix. Okay. So, combining these two colored portions, you get n square minus n elements. Okay. So 1/2. So in the upper part, we get n square minus n by 2, half of the number of elements, half of the remaining number of elements are present in the upper part, and lower part contains n square minus n by 2 elements. So that if we add them together, we get n square minus n elements, non-diagonal elements. Okay. Now suppose you are designing a relation. You want to design a symmetric relation. What do you do? Now all these things, I'm writing one particular element over here for your better understanding. So for example, I'm writing here, just a minute. These blue colored portions will not be, let me draw it properly. Some mistake is there. The colored portion will be from this. This will also be included. Okay. This part will also be included. Now you see, look at these elements. In these elements, just a minute. Again, one mistake I have done. Actually, since I have not written all the elements properly, so actually this will be like this. Yeah, that is the thing. Now this particular part will not be present because it is the diagonal element. Now this is the upper part, and this is the lower part. Now you want to design a symmetric relation from these elements. What will you do? You can see, you can check that all the elements present in the upper part have its twins present in the lower part. So if your relation is to be symmetric, then with a1 comma a2, a2 comma a1 is, if you say that I have a relation which is symmetric, what does it mean? It means that a1 and a2 and a1, both the twin brothers, are present in your relation. a1 comma an and an comma a1, both of them are present in your relation. So all the twins are actually considered to be present in your relation if you declare that your relation is symmetric relation. So actually you will constitute a symmetric relation, we must consider these n square minus n by 2 elements first. Not n square minus n elements, because n square minus n by 2 elements, because if a1 and a2 and a2 and a1, they will be same because your relation is symmetric relation. Okay. Just like equality, when equality is a symmetric type of relation, when you say that a equals to b, then it automatically becomes b equals to a. So we have to consider all these elements first of all to design a symmetric relation. Not only this, if we consider this, not in the previous example, we considered these elements as a set together, because to be reflexive in every relation, entire delta S must be present. But in the reflexive, in the symmetric case, it is written, if one is present, its counterpart must also be present. Okay, so you can design a symmetric relation where you have considered all these n square minus n by 2 elements along with just a1 comma a1. Because if a1 is if you consider a to be a1 and b to be a1, then ab is present means ba is also present. So how many such elements are present over here? a1 is present, a2 is present, n is present. So n elements, n diagonal elements has to be considered also to make your relation reflect symmetric, because I am counting the total number of reflexive relations. I am counting the totality of this. So along with this, we also have to consider we also have to consider n diagonal elements. And in total, with these n square minus n by 2 plus n elements, that is n square minus n plus twice n by 2 elements, that is n square plus n by 2 elements, we can form 2 to the power n square plus n by 2 symmetric relations defined on the set capital S. So the answer is, the conclusion is 2 to the power n into n plus 1 by 2 symmetric relations can be defined on capital S. Remember this result also. It is also very important for your examination purpose. I am giving you one problem, example number 3. Try to find it by yourself. How many relations which are both reflexive and symmetric can be formed on capital S? This is a question for you. Try to find out the answer and just don't Google it. In Google, you can get answers. Okay, the result is present. But I'm actually asking you to do it by yourself. To do this kind of problems, what you have to do is that, since I'm teaching you right now, I'm doing it in generalized way, okay, by considering n elements. But if you are doing something new by yourself, the strategy is consider small sets with 2 elements, with 3 elements, with 4 elements. Do some mathematics on it. I know you are a very busy person because you are doing computer science. You do not have any time for doing mathematics, probably. So find some time if you have and do these small things on these small sets. And once you do it, after that, you try to generalize your process for n different elements. One another part is that do not try to find out how many transitive relations are there, because it cannot be found. It is very difficult. It cannot be found. There are some problems while for finding out the transitive relations, because you will not be able to find it out. Difficult, very difficult. It cannot be said. So do not waste your time to find how many transitive relations are present. Just remember how many symmetric relations can be formed. I have already told you how many reflexive relations can be formed. I have already told you. And try to find out how many symmetric and reflexive relations. A relation which is both symmetric and both reflexive can be formed from this particular set, on this particular set. Okay. So very important result. Now I'm going to talk about a special type of equivalence relation. It is also very important. So let me give you the problem. Okay. fix a positive integer small n in Z. You know Z is the set of integers. Define a relation, on Z. Define a relation on Z as follows. Define a relation on Z as follows. For all A, B belonging to Z, A is related to B if and only if n divides A minus B, that is okay. We are going to check whether this relation, is a equivalence relation or not. Okay, so let us try it quickly. Time is also running out. First of all, we see that n divides A minus A, because A minus A, this number can be written, this is 0, and that number can be written as n into 0 for some integer, 0 in capital Z. So A is related to A, which implies is reflexive. Number 2, suppose A is related to B, which implies n divides A minus B. This implies A minus B can be written as n into k for some integer k belonging to Z. This implies B minus A can be written as n into minus k for some integer minus k belonging to Z. And this implies B is related to A, which means is symmetric. Okay. I'm going to the next page. Let A is related to B, and this is n, and B is related to C. This implies n divides A minus B and n divides B minus C. This implies A minus B is equal to n into k1 and B minus C is equal to n into k2 for some integers k1, k2 belong to Z. This implies A minus B plus B minus C can be written as n into k1 plus k2. This implies A minus C is equal to n into some k prime, where k prime equal to k1 plus k2 belonging to capital Z. Therefore, A is related to C, which implies that this is a transitive relation. Okay, therefore, the relation this is reflexive, symmetric, and transitive. This implies that is an equivalence relation. Is an equivalence relation, and if it is so, we write A is equivalent to B, which means A is equivalent to B mod n. Okay, or B is equivalent to A mod n, whatever. Okay, so I'm writing here, I'm not going to the next page. Also, it is written sometimes as A is equivalent to B mod n, or B is equivalent to A mod n, whatever. This relation is called, has a special name. This relation is called congruence relation. And it was first discovered by the Prince of Mathematics, Gauss, in his book Disquisition in Arithmetic. Okay, this congruence relation gives congruence class, and this congruence relation is very important to study group theory, study of groups, rings, fields, and Galois field. Okay, which are very important for I mean, computer science. We will not be able to understand that how it is how it is important, because you have to move stepwise. You have to reach to Galois field, and then you will understand that you'll be able to look at the applications of these things over there. Right now, to some people these things may become Hebrew. What sir is doing some kind of abstract mathematics, non-interesting mathematics. Consider it to be non-interesting. Since it is there in your syllabus, do it and learn it. Then you can forget it, and then whenever it is required, you can come back to my lecture videos and books to again to recall the ideas once again. So I have already defined the congruence relation in today's class. There is no time. No third session will be taken today. In the next class, I will discuss further on this particular type of relation, which is called congruence relation. Okay, so see you next week on next Monday. Till then, bye.